The binomial distribution is a model for random processes that involve binary variables, that is, variables with results that could be written as yes or no. It describes the probability of having x successes in a sample of size n. If the probability of success on any one observation stays the same, and the observational units are independent. To make sure that the observational units are independent from a sample from a random process, there are two major ways to do that. One is to make sure that the order of the correct outcomes is randomized. For example, we might flip a coin to decide which of two signals to send to a dolphin. That makes sure that the dolphin isn't just guessing that we're going to fall into a pattern of left, right, so that the correct answer on the second trial depends on what the correct answer on the first trial was. The other major way to do this is to make sure that the observations are spaced out in time. For example, if we were taking a sample of the weather on different days, we wouldn't want to look at whether today was sunny and tomorrow and the next day, because the weather on two different days that are right next to each other tends to be similar. Instead, we would want to take a sample of days, say every 10th day, which tends to be more close to independent. To decide whether a binomial distribution is going to be useful, it's often helpful to think about whether we could simulate a sample using a series of coin flips, which might be biased. If x would be the number of heads from that set of coin flips, then a binomial distribution is likely to be useful. If the number of successes x follows a binomial distribution, then we can compute the probability of getting exactly little x successes by taking a constant times p to the x times 1 minus p raised to the n minus x, where p is the probability of success on any one trial and n is the sample size. Notice that what we're doing here is taking the probability of one success and raising it to the power of the number of successes. Similarly, using the complement rule, the probability of one failure will be 1 minus the probability of one success, so 1 minus p. And we're raising that probability to n minus x. That's the sample size minus the number of successes, so overall that's the number of failures. It makes sense that we would be multiplying these probabilities because the binomial distribution is based on the multiplication rule for independent events. We're requiring that each observation or trial be independent of each other observation or trial, so we can multiply their probabilities. Finally, the constant is the number of ways to reorder x heads and n minus x tails. For example, there are 3 different ways to order 2 heads and 1 tail. So if our sample size is 3, then the probability of exactly 2 heads would have a constant of 3. It's nice to know what this constant represents, but in practice, you'll always use a calculator to compute it. Here's how to compute the probability that the number of successes equals some specific value little x on a TI-83 or TI-84. You're going to press the second key and then the VARS key, and then select Binom PDF and press enter. I like to think of the P in PDF as representing a particular value, because we're finding the probability that x is exactly equal to the particular value little x. Then the order of the arguments is n and then p and then x. So the sample size, the probability of a success on one trial or observational unit, and then the desired number of successes. Depending on what kind of calculator you have, you might need to enter a comma in between these values. And the comma key is above the number 7 key. So for example, if we wanted the probability of getting exactly 3 heads when we toss 4 fair coins, we would use binom PDF 4, comma 0.5, because that's the probability of heads, comma 3. If we want to compute the probability that x is less than or equal to little x, we could compute lots of separate probabilities. Say that x is equal to 3 and 2 and 1 and 0 and add them all up. But there's a faster way to do this on our calculator. After we press the second key and then the VARS key, we can select binom CDF and press enter. I like to think of the C in CDF as standing for combined, because we're finding the combined probability that x is equal to or less than little x. The order of the arguments for binom CDF is the same as the order of arguments for binom PDF. Finally, we can also compute the mean and standard deviation of x. If x follows a binomial distribution, then its mean, or expected value, is n times p, where n represents the sample size and p represents the probability of success. And its standard deviation is the square root of n times p times 1 minus p. You might also see these written with a pi instead of a p. It doesn't really matter as long as you're multiplying the sample size times the probability of success for any one observation.